Let's look at another tutorial where we try to look at conduction only, but there is not a single zone, there is a, let's say, multiple zone. In multiple zone the conduction is happening. So let's say at one places, let's say there is a top part, there is a bottom left, bottom right. Okay, so and at one places we specify the constant temperature, and on one places we specify constant heat flux boundary conditions, and there is a interface in between, and for each of these slabs the thermal conductivity is different for each of this area. Okay, and here also we specify in this zone, let's say 473 K, and heat flux, okay, heat transfer coefficient equal to 100 watt per meters square Kelvin. Okay, so this is the our test case, and we want to set this test case inside the OpenFOAM. So this is, now we are working with the multiple zones, so we have to work with the multiple CHT, multi-region simple form. Okay, so first look at that particular solver, and then we go toward the tutorial area. So heat transfer CHT multi region form. Okay, so that is the place, and inside that we have a CHT simple form. Okay, so when we talk about the CHT simple form, we have a couple of the things. It is a steady state multi-region solver first of all. Okay, and it try to work with the multiple zones basically. Okay, and if you look at the flow algorithm, it is rely on the raw thermo class of the things. Okay, and we have a different type of the region property we have to specify. We have a solid thermo, we have a fluid thermo, radiation also you can activate. Okay, along with that we try to solve for multiple fluids and multiple solids. Okay, if you don't have any fluid zone, and then this part going to be skipped. If you only have a solid zone in the present case, that means we are working with this portion of the code only. So here what we're going to do, we try to look at the multiple solid zone. So when we talk about the solid zone, here we have a solid equations, that is what, nothing but our energy equations, that is what we are solving here. Okay, so in terms of enthalpy we are solving the energy equations. Okay, and if we look at the energy equations, along with that let's look at the its control. So we require only non-orthogonal simple control options only along with that. Okay, so right now we are not exploring about the fluid part, we are looking at only the solid options. So where we going to take into account the energy equations, okay, with the help of the very simple this class of the test case. So let's explore how one can set this test case inside the OpenFOAM. So here is tutorial number 2. Okay, and let's look at, so first let's clean the test case. So let me go to the area. Okay, and first let's clean the case. Okay, now block mesh. Okay, so and just check how the mesh is look like first. Okay, so this is the mesh file we constructed. Okay, we don't have a till now any zone or anything, and we require the 3 different zone 1, 2 and 3 because we want to work with the multi zone. Okay, and for each zone we have a different property, and we try to solve each zone with the help of the simple energy equations. That is the idea. Okay, so what we're going to do here. Okay, so we have to first use this mesh and try to construct these multiple zones. So for that we have a topo set options available, so just explore. So we say, let's say inside the topo set we say solid, left solid, okay, then right solid, and we said top solid. So that is nothing but top solid, left solid and right solid. So we try to construct this top solid and left and right solid with the help of the topo set options. So just look at, we have a 0, 0, minus 1, 0.6, 0.6 and 0.25. okay, so this is what we have. Okay, so 0, 0, 0 and this corner, so point in the y direction 0.25 meter and in x direction 0.6 meters. So we try to patch this area as a left solid. Okay, then right solid 0.6 till this one, so from 0.6 that is starting point, and this corner is 0.9 and 0.25. okay. That is what exactly here 0.9 and 0.25. And then top x wise it is, sorry, x wise it is 0, okay, and but y wise is 0.25, okay. So 0.25, and that corner is 0.9 and 0.5, okay. So that is how we able to construct the topo set and try to create the our different solid. That is the first thing we going to do with the help of this box. So let's run this particular command, okay. So that is available here. So after that we are running this topo set, okay. So let's look at again the paraform, different sets included. So look, we have a now left, right and all the solids zone available, okay. So this is here left zone, okay. Then we have a right zone and we have a top zone, okay. So this is 3 zone we constructed with the help of the topo set command. Fine. Then we just constructed this zone. Now let's split the zone, okay. So we have appropriate cells ready to go. That is the idea we have. So we split the zones, okay. So we have a cell zone 1 2 3, okay. So when you say cell zone 1 2 3, what going to happen? It's happened that inside the 0th folder it also try to generate these all 3 folders, okay. So that is the what one can look at from here, okay. And here just check condition wise. So we say in the temperature Ymax, okay. So that is the Ymax value, okay. So we say external wall heat transfer temperature, okay. So that is we specify with the kappa solid thermo, okay, and Q equal to 150, okay, and value that is dummy value equal to 300, and that value about the kappa, that is the thermal conductivity we are going to take from the solid thermo portion. Then x mean, okay, that is here we say 0 gradient conditions, okay. Then x max, okay, we say some particular temperature 473 degree kelvins, okay. Along with that we say external wall heat flux temperature kappa solid thermo, H we specify 100, okay, here this one, okay. Along with that we have a dummy value, okay. So that is how we say temperature and the H, or we can say directly specify the Q, okay. So 2 options we have to specify different class of boundary conditions, okay. Then minimum, okay, that is Y minimum, okay. So that is here that we have a constant external kappa, okay, and T 275, H equal to 5 and value 300, okay, and Z empty, default is empty, okay. So that is what we specified here as a boundary conditions, okay. And pressure is dummy, so we say internally calculated, okay, because anyway we're not going to solve any fluid flow class of the things here, okay. So it is pure conduction, okay. So but that entry is required, so that's why we are keeping this as a dummy entry. So now we have multiple zone, okay. So we have a boundary condition for all the peripheral thing, but what about this interface condition? So we have to look at this interface conditions. So for interface conditions we have to rely on this particular directory change class of the options. So what we did here in the system folder, as many zone you have, let's say left solid zone, and here we constructed the directory change, okay. So look, in the directory change we say left solid to anything, it's that means wherever we have a coupling boundary condition, so left solid to right solid, left solid to top solid, okay, that is the coupling boundary conditions, okay. At that all the locations what we required, that means where exactly it's going to modify, it's going to modify in 0th folder left solid. If you look at this condition at present, okay, so it is, look, this left solid and the right solid, we don't have any condition here, so we have to specify these coupling conditions, okay. So that is what we needed. So for that we are relying on change directory. So we say left solid to left solid to right solid or left solid to top solid, both the places we want to replace with the help of this compressible turbulent temperature coupled baffle mixed, and we say temperature is reference temperature. Kappa we going to take from the solid thermo, okay, and this is all the dummy name, okay. So from the solid thermo we try to take into account the kappa value in the respective way, okay. So that is what we are saying, the neighboring condition. So what exactly going to happen, what condition going to satisfy? It says that temperature, let's say coupling between left and the top. What going to happen here? They try to enforce two condition. Temperature very next to the cell, that is inside of the left, this portion is equal to the temperature equal to this cell, as well as gradient del T by del N into thermal conductivity equal to del T by del N into thermal conductivity of this area. So these two conditions they try to enforce on this line. Same way here also. So what they're going to do, whatever the cell very close to this side, okay. So what they say, temperature of this cell equal to temperature of this cell, along with that K del T del N of this cell equal to K del T del N this side. That is the interface conditions, okay. So that is the standard interface condition. If you look at any of the heat transfer book, that is available, okay. So that is what we try to enforce with the help of this class of enforcement. So after you run this particular check this options, let's look at what going to happen. So we are running on the left solid, okay. So if you run on the left solid, now if you open this, okay, reload, so look, this is what we copied. Either you use this change directory options, or you can manually also edit these files, okay. So it is better to work with this check directory class of the options. Now in the similar line we have a options for the right solid, and for that also the same thing, right solid 2. So right now we didn't change the right solid area, so just look at in the 0th folder at the right solid and the T file, okay. So look here, right solid to left solid and right solid to the top solid. So this portion we supposed to use as a couple boundary conditions, and for that we are again using this one change directory options, okay. So the test case setting is only little bit tedious, otherwise it's very easy to simulate it, okay. Sorry, what happened, I use for right solid, correct, okay. So let me open again this file, okay. So look, it is changed. Same way for the top solid as well. So top solid, okay. So top solid also have a top solid to right solid and top solid to left solid, okay. So when you run one command about the top solid, it going to change the nomenclature here, okay. So let me open it again, and then we try to explore what exactly happened at this location. So we have a top solid to right solid. Now again go back to the, let's say this is about the 0 folder, and this is about the left solid to top solid. So look, left solid to top solid we have a this condition. Same way from top solid to left solid we have a conditions, okay. What it going to do, it try to enforce the neighbor as a temperature, so it try to enforce the neighbor from the left side, and here it try to enforce the neighbor from the top side, okay. So in similar line, with the help of the kappa, that is the thermal conductivity from the solid thermo, we try to explore and try to plug the interface condition, the temperature both the side equal and the normal temperature gradient and thermal conductivity is also enforced to be equal, okay. So that is what we needed. Now let's explore the how we set the different zone property. So in the solid here we have a, first of all we have a this region conditions where we don't have any fluid, but we have a 3 solids, okay. So if you have fluids, then you can use the fluid here, and when you say fluid, this zone is start working out, okay, inside the multi region simple form. But right now we only have a solid, so left solid, right solid and the top solid. So first left solid, then right solid and the top solid going to simulate, and for each of the solid we have a different properties. If you want to set, then it is here, okay. So left solid, look at the thermo property for left solids, okay. So here it is because it is a solid, okay, so we have a H solid thermo, okay, and from H solid thermo we have all this is dummy value, we have only kappa, okay. So kappa, how much we want? For left solid we require 200, so here change it to the 200, that's it. All other value are the dummy value because we're not solving any fluid flow. In case of the fluid flow all this value is required, but right now we don't solving for fluid flow, so we require only out of this only kappa value, okay. So that is what we set here. Then in the similar line just look at the kappa for right solid, okay. So for the right solid the kappa value what we required is 5, okay. So what I'm saying is this is the K as a kappa thermal conductivity, so we required as a 5, okay. So here we set for left. Now look at for the top. So for the top here it is value is 0.5, so what we required is 0.2, so just change to 0.2, okay. So we set with the all the properties whatever required. So what we have to set, we have to go to the individual folder inside the constant directory and set the thermophysical property, and here only important is this zonal property, all these are the dummy values, okay, or not required at all, but we must set this set it region property setting, either how many fluid or the solid zone we have, okay. Depending on that it going to simulate the test case, okay. So that is what exactly happening. Now just check few more things from the system folder, okay. So in the system folder also we have a different schemes for each of the solid portions. So normally it's supposed to be same, okay, but if some portion has a large gradient you can change or tune the parameter. So we are working with the enthalpy equation, so enthalpy equation we're going to solve, okay, and no non-orthogonal character required, okay. In the similar line for scheme, okay, steady state we require the simple linear, gauge linear, and the uncorrected, all these things, okay. So this is very easy to set. So but idea is that we have to set for each and every zones, okay. So now this is all the dummy value, okay, except control dict file. So for each zones we have separate FV scheme and solution files, so we have to set all these files, and if we don't set it, it gives us the error, okay. So that is what we have. Now just look at the control dict file. Our solver is MHT multi zone simple form, okay, and we going to work for 300 iterations, okay. So let's simulate the test case and have an idea how exactly it is working. So multiple this thing, okay, so it is done. So let me first look at the file, okay. So it give us the idea what exactly happening. So what it did, create the mesh for zone, all the zones left right, this thing, okay. Now reading the thermo package, okay, for okay. So left solid, read solid mesh thermo property of the region solid. So for region solid it read the test case, okay. Same way now for right solid it try to read the all the property, then top solid it try to read the property, okay. For as many zone it try to read the property, then time step start. First we say left, so it try to solve the governing equation in the left solid, then right solid, and then for the top solid, okay. And we also explore the mean and max value, okay. In the similar line it try to solve for each and every solids, okay. Now so at the end what we get, it in each of the solid it converged, okay. So in each of the solid it converged very nicely, okay. So that is almost taking the 0 iterations, so it's almost it converged very nicely. That is what we see. Now let's look at the result, how exactly it's look like. Now look, we are working with the multi zone, so we not able to do the post processing with the paraform, so we say paraform and the touch all, okay. So that is what we require. Then it try to construct this left right and dot OpenFOAM part, and then you say para view, and through the para view we have to see the all the results, okay. So it is little bit different. In the para view try to open all these options, okay, apply, Now if you don't want to see these options, just say, and here activate the temperature, each places activate the temperature. Okay, now just look at the temperature how look like in this area as well as in this area. Okay, now go to the last iterations and check. So this is the temperature distribution. We have constant heat flux boundary condition at the top. Okay, so this is how heat transfer is varying. Okay, so 1, 2 and 3. So if you want this area, just check how it look like. Okay, so this is the area. Okay, and our thermal conductivity is very high, K. Okay, so that is why you don't see much difference here. Okay, so this is the different zone with the different thermal conductivity. You can set very quickly, but idea is that we have a multiple zones, so for each zone we have to set a couple of the things. So I will repeat again. For each zone, what is required? First thing required is the different boundary conditions. So in between this interface we require the set interface condition in between two zones. So that's why we have to use this change directory option. So it is very handy to change the directory, all the boundary condition at a time. Okay, so that is what we explore here, and with the help of that we quickly try to set up a different interface conditions, interface condition for different zone very quickly. So that is one thing. So without that we cannot start the calculations. Okay, so if we look at the readme file, this is split zone, it's fine. Okay, so this is about the creation of the mesh, and then this is the zone property, change directory allow you to look at the interface boundary conditions. Okay, so that is what needed. Okay, so that boundary conditions is required. Okay, and then what else we require is in the constant folders, for each of the solids we supposed to specify the different zone conditions. Okay, so if we don't specify appropriately, it will not give us the proper results. So depending on our requirement, we can specify each zone different properties. Okay, and this is very important, region property, where we say the solver how many fluid zone and how many the solid zone is available. Okay, so when we talk about the heat exchanger class of the calculation, at that time we have a here fluid zone as well, and fluid and solid interface we try to achieve. Okay, so at that time we try to explore few more options, but this is how very quickly one can look at this multi-zone class of the calculation inside the OpenFOAM. This is still the pure conductions. Okay, so that is what we are looking at here, the pure conductions, and for that we have a couple of conditions available. So we have a external wall heat flux temperature, kappa solid thermo. Either you specify the Q or you specify the ambient temperature and the heat transfer rate. Either of the things is going to work. Okay, so then you have a this value. Okay, you can specify and it going to work very neatly. Okay, so that is what we look at very quickly. So this is very simple test case. Okay, now let's explore few more entries, few more different class of the test case